Okay, we're going to get in the Wayback Machine and go back 25 years to 1997 when Comet Hilbot graced our skies. It has been the brightest comet in decades, and we haven't seen anything that bright since. It was actually discovered in 1995 by these two gentlemen, Alan Hale on the left and Thomas Bopp on the right. Alan Hale he's an actual astronomer. He was in New Mexico, but he also does a lot of sort of amateur astronomy. He was checking out, looking at comets and things. And on that night, he was waiting for one comet to rise. So he thought he'd look around at deep sky objects, and he looked at M70 in Sagittarius, which is a globular cluster. And in the same field of view, there was this little fuzzy object. Well, about the same time, Thomas Bopp, who was in Arizona, was out with some friends of his. They were doing some observing. Thomas Bopp didn't even own a telescope. And he was looking through his friend's telescope at M70, and there was this fuzzy object there. And it was like 10th magnitude. And they both, watched it for a while and determined, yeah, this thing is moving. It's an actual comet. So that got reported. And it got reported, and then let me go to the next slide here. The orbit was determined to be really strange. The comet, when they discovered it, was out past, it was between the orbit of Jupiter and Saturn. And back then, in those days, when it was people discovering comets and not telescopic surveys, most comets weren't seen until you're get close to the orbit of Mars. And yet they were seeing something that was past the orbit of Jupiter, and it was like 10th magnitude. And so orbit was calculated, and it's almost, this isn't a real great image I have here, but it's almost 90 degrees to our plane of the ecliptic. And it actually, it's coming in, it never really got that close to the sun. It got about 1 AU, which is, the Earth's average distance to the sun, which is about 93 million miles. And that's about how close it got to Earth also. And then it passed between the orbit of Earth and Mars, but Earth was way over here by then. But the reason it was so bright is because it was so big. Let me go back. Let me go. Yeah, so it turns out that they calculated to be that bright from that distance. It would have to be, the nucleus would have to be somewhere between 24 to 48 miles across. And if you look at in this image, you see all these other comets that the spacecraft have flown by, and look at the size of them. They're all 4 or 5 miles, 3 miles, a couple of miles across. And, think on the order of something like, a good sized chunk of Mount Diablo. That's about their standard size of a comet. But Hellbop, they figured at least, 24, 48 miles across. The thing was a monster. Let me go back a little bit and talk about basically what a comet is. I know most of you probably 25 years ago probably saw the comet at one time or another. But a comet basically orbits the sun, and it spends most of its time very, very far away. And so it's made up of rocks and ice, and ices of gases that are so cold that they're frozen solid. So when this thing starts getting closer to the sun, instead of being, whatever it is, 400 degrees below zero, all of a sudden it's 200 degrees below zero when it faces the sun. And so all these frozen gases instantly vaporize, and they end up just shooting off, basically exploding and carrying parts of the nucleus with it. And so that forms your coma, and then solar wind and magnetic fields of the sun cause the tail to form. So, like I told you, that it was discovered in 1995, but it wasn't until 2 years before it actually got to us. In the meantime, another comet that was discovered right at the start of 1996, and a couple months later, basically flew right past us, Comet Hyakutake. And the thing with this comet, it was fairly small, but instead of being 1 AU away, it was 0.1 AU away, which is more like 9 million miles where it passed the Earth. And I remember one time up on I think I took this photograph here, and this is the old film cameras. We were up on Mount Diablo, and you could easily see the coma of the comet, and but to get the tail, you had to use your averted vision, and all of a sudden you could see this long tail that extended for several degrees. And so that happened in 96, about March of 96. And so the next year, then we had Hailbot come through. Showed up in the morning sky, and it was mostly everybody that lived north of the equator got a pretty good view of it. It stayed in the northern sky most all the night. This was got it in the early morning sky here. And the thing about this comet was they were so bright that, you didn't have to have binoculars to find it. You didn't have to have star charts to find it. You just walked outside, looked up, and there it was. It was visible with a naked eye figured as something like 18 months. And for several of those months, it was brighter than 0 magnitude. So this was a shot I did. Actually, I got myself in the shot. I had set my camera up to take a time exposure. Then I ran back and sat in front of the telescope for a few seconds, then ran back and triggered the shutter again. It's probably like a 20 or 30 second exposure. But what was neat about this is you can see that it had quite a long ion tail, a blue tail, going off to the left there. And it also shows you that just about anybody that could, if you had a camera, you could get a picture of it. It wasn't that hard to photograph. So this, in 97, people were just starting to get into CCD imaging. And so when this picture came out from some guy named Tim Puckett, he had several of these pictures where he, using a CCD camera, seeing all kinds of detail in the coma and stuff that you weren't picking it up on the regular film cameras. And I remember seeing this picture on the internet, which is just starting to come into use, where most people were all these pictures were being posted on the internet, and that was kind of a new type of thing. And all of a sudden you could see what the camera looked like every single day. So this is a picture taken by Marnie Benson. She went down to Death Valley and took a pretty nice picture. A telephoto lens there. And there's another one of her pictures over, it was over Death Valley. So I like it. It looks pretty good. So we did have, I do remember, and maybe some of you do too, that we had some nights up on Mount Diablo when the comet was high above. And here's one above all the city lights. And here's one above the tower most of you probably recognize. I do have one anecdote to bring up about Mount Diablo. There was one night where we had the Comet Hilbot, and we also had a lunar eclipse going on at the same time. And a lot of people were going up, a lot of public were going up to the mountain to see it. And I got running a little late, and I started going up the mountain when it was already starting to get dark, and it was bumper to bumper all the way up to the top. And so I got to that, that stopped the traffic up to that big area where the last mile or so, where you make that big sweeping turn, and then you go up to the summit. And they had all these people parked there, and the ranger was saying, hey, we can't take any more people. And everybody was, whining and complaining because they couldn't see through a telescope. And I raised my hand and said, hey, I got a scope. So I set my C8 up, and I probably had like 100+ people looking through my scope that night. Also talking to other rangers and stuff, and they were talking about how many hundred cars they had come through there, and they thought at the time there must have been somewhere like 1,500 people on the mountain at one time. So I think that was probably the biggest draw ever on that mountain. So as y'all know, comets, superstitions about them in the in history, they cause disasters, wars, tragedies, and what have you. And this comet was no different. We had apparently an amateur astronomer had photographed the comet one time, and there was a star right next to the nucleus, and it wasn't on his star chart. So somehow the word, he published it or something, the word got out, this is unknown, and then it became an alien spacecraft following the nucleus. And then that's all that was needed for a group called Heaven's Gate. They were looking for a spacecraft to come and save them or something. And in the end, you guys can go look it up, but there was over 30 people committed a mass suicide, and it was just, it was pretty awful. But this stuff seems to come up every time there's a big comet around. And the other real sad thing was Thomas Bopp, one of the discoverers of the comet, his brother and sister-in-law unfortunately were killed in a car wreck. One of the weeks that the comet was the brightest, they had gone out to do to photograph the comet, and I guess they never got quite back home again. And he said that started out as the happiest week of his life, and it turned into the worst week of his life. So things happen. So comet won't be back for another 2,500 years. So I'm sure we'll see a few more comets between now and then, but this was a really bright one, a really big one. And I think, like most of you, I'll always remember this comet. So that's everything I got. Any questions?
Appreciate it. Yeah, we got any questions here? No questions? Oh, come on. All right. Okay, well, I got one for you. The reason I was able to identify that comet is because I did a fairly extensive look at it myself. I was doing some work up in Allegheny, California for a period of time. And up in Nevada, before we get to the Allegheny, we stopped at Nevada City, and there's a little airport up there in Nevada City. And so, oh, okay. So it was a nice, clear, flat area, beautiful place to take pictures of the comet in the morning. So somebody had a question here, and
that was, the question is, was it Hyakutake or Hailbot that returns in 2,500 years? It's Hailbot.
Yep, Hellbop.
Yeah, actually, Hailbot was in like a 4,000-year orbit, and then like the last time it came through before this time, it passed close to Jupiter and it knocked it down to 2,500 years. So,
yeah, that big planet out there has got a big reach.
Yep, that's for sure.
Yeah. Oh, Kent. Oh, do you happen to remember the period of Hyakutake? I don't offhand.
No, you'd have to. You can look it up. I don't know what it is.
Yeah. I mean, I'm not even sure if it was projected to be able to come back. As I think, as you pointed out, it was a small comet, and I'm not sure if there was much material left because it was so close in. toward
Yeah.
the sun. All right.
I had a
Oh,
footnote.
oh, sure.
You should all be
Go ahead.
familiar with Halley's Comet. It
Mhm.
has a period of about 75 or 76 years. Unfortunately, I wasn't able to see it when it last appeared. However, the year that Mark Twain was born, it appeared. The year that he died, it reappeared.
So you missed both of them.
Trivia.
Mhm. Oh, Randy came up with the answer for the question. It was, what was the period of Akitake? It was 72,000. Yeah. So,
What's the closest the comet has ever come to the Earth?
okay,
What's the closest a comet's ever come?
yes,
Is that the question?
that's the question.
There was a comet, and it was probably about in the 80s, that passed, it probably was within like a million or 2 million miles. It was discovered by a infrared telescope that's in space. And I can't remember the name of it. And you could see it, but it was very faint. It was just a big hazy ball. That's all I remember seeing.
Mhm.
It was pretty small. Small.
Well, he's asking, was it a small comet? And
Yeah, it would have to be.
must have been, it sounds like it must have been because it was faint. And if it was that close and it was that faint, then yeah, there's probably not much to it, so. Oh, and Randy John's got another answer here.
That's the one.
Rocky Alcock. That's
Yep.
it's a complicated name. But
Well,
that
the
would
IRAS
happen
is
when
the
you get-
satellite part of it. It's the infrared satellite.
Yes, oh, that's right, yes, that's right. Wikipedia's, yeah. Okay, and Dr. Basri has a comment, and that is, I think we passed through the tail of Haley 2 times ago, not sure though. Nicholas would have been further. Okay. Let's see if anybody else asked anything. Okay, oh, that's right, yes, infrared astronomical satellite, yes. Okay. Oh, hi, how you doing? We got another question here.
Wasn't Tunguska a comet fragment?
Could have been. I don't know.
Yeah,
I
they,
never found anything that related to a meteorite.
yeah, that was the suspicious part of it. It didn't really have a crater as such, but yeah, there was certainly a lot of debris and radiating away from a central point and things like that. So
Like
yeah,
an air blast, basically, yeah.
exactly. Yeah. Well, I mean, we had Chelyabinsk, which was a meteor.
Yeah, there
And
was
then,
a comet.
well, I don't think it was related. I don't think it was related though. I think they determined, that was my recollection. I could be wrong. Oftentimes am. So, but yeah, again, one of those things we can check out on Wiki. Anybody else have any question, comment? Okay, all right. Well, thank you, Mike. We appreciate it. That was a nice flash from the past. Thank you, Mike. Get started with tonight's main talk, which is entitled "Are Red Dwarf Exoplanets Habitable?" I'm pleased to introduce Dr. Gibor Basri to our meeting. Professor Basri received a Bachelor of Science in Physics from Stanford University and a PhD in Astrophysics from the University of Colorado Boulder. An award of a Chancellor's Postdoctoral Fellowship then brought him to UC Berkeley. He joined the faculty, I always do that. He joined the faculty of the Berkeley Astronomy Department in 1982 and became a full professor in 1994. A high resolution, this is a good one for you, spectroscopist. He was an early pioneer and expert in the study of brown dwarfs, as well as star formation and stellar magnetic activity. He has extensively used telescopes at the Lick and Keck observatories, along with the space telescopes as well. Professor Basri was a co-investigator on NASA's Kepler mission, which revolutionized our knowledge about exoplanets. He is still active in research despite being officially retired. So please welcome Dr. Basri.
Thank you very much. And thanks for inviting me back. I did give a talk to you folks a number of years ago. I'm assuming that my screen is visible. Is that correct?
Yes, sir. Yes, sir, that is correct.
Okay, great. Okay, so I wanted to talk today about the question of whether planets around red dwarf stars are habitable. This is a very hot question at the moment. I'm sure you all have been following the announcements of Earth-sized planets in habitable zones around other stars, and may have noticed that most of those are actually Earth-sized planets in the habitable zones of red dwarf stars. But it's not completely clear whether they're actually habitable, even though they're in the habitable zone. And so that's really what I wanted to talk about today. I think that I'm probably able to take questions as the talk goes along. If you interrupt me, I probably can't follow the chat. So if you want to jump in, or if somebody wants to watch the chat, I'll try to do that. Okay, so let's see. Here we go. I apologize if everyone's already familiar with all of this, but usually not everyone is. So red dwarfs are actually the most common kind of star in our galaxy. About 3/4 of all stars are actually red dwarfs. The GIF on the left there that's rotating shows the nearest few parsecs away from the sun, which is at the center of that. And all the red dots are red dwarfs, and you can see there's a few other colors, but clearly the red dwarfs dominate the population. You can see that in this graphic over on the right as well. And they have a number of other interesting characteristics, one of which is that they're much longer lived than our sun. So no red dwarf that's ever been born in our galaxy has died. And in fact, that'll remain the case for another 10 times the current age of the universe. So they're very long-lived stars. They're very stable. Once they settle down on the main sequence, they stay there for hundreds of millions of years. It also turns out, and this is a result from Kepler, that smaller stars tend to host smaller planets. And in this context, the Earth is a small planet. And so they probably host most of the Earth-sized planets in our galaxy as well. And consequently, given the fact that there's so many red dwarfs and so many Earth-sized planets around them, they're the main action in terms of Earth-sized planets in the habitable zone. The stars themselves, well, they're called red dwarfs because they're red and small, and that's because they're somewhere between 1/2 and 1/10 the size of the sun and the mass of the sun. Size and mass go pretty well together in this regime. They tend to be less than half the surface temperature of the sun. So instead of 6,000 degrees Kelvin, they're more like 3,000 degrees Kelvin. And the main difference is they're much fainter and much less luminous, I should say. So they put out, their output is somewhere between 1% and 1/10,000th the output of the sun. And so that means if you want the planet to receive the same amount of energy on its surface as the Earth does from the sun, the planet has to be a lot closer to the red dwarf. So here's just one graphic where you have the solar system down here, and here's a red dwarf planetary system that all fits nicely well within the orbit of Mercury. And the planets that are habitable are way in there like that. So we're going to come back to that topic again. Well, one of the reasons that you keep getting announcements of red dwarf habitable planets is they're actually the easiest ones to find for a few reasons, despite the fact that the stars themselves are faint. Red dwarfs, there are two main ways of finding planets. One is to use the wobble method or radial velocity method, and red dwarfs will produce the largest radial velocity signal for a given planet at a given distance because the star itself is smaller in mass. So the planet is able to pull the star around, harder at a given size and mass. So that's one reason. So they're easier to detect in radial velocity, and they're also easier to detect in the transit method. I'm going to come back to these two methods in a second, but they'll produce the largest dip in the light if they pass in front of the star, because again, the star is smaller. So if you have a planet of a given size, the planet will occult more of the star since the star is smaller. So that makes it also easier to find. And then the final thing is as I said, the habitable zone of red dwarfs is much closer into the star, which means the planet orbital periods are much shorter, so they'll come around more often. And that makes them easier to transit, and it also makes it happen more often. So all of those things mean that it's easier to discover habitable planets around red dwarfs than it is around solar type stars. And that's one of the main reasons why you keep getting those announcements. The other reason being that there's just a lot more of them. So, here's a few of the habitable Earth-sized Earth-sized planets in the habitable zone around red dwarfs, and you can see the distances to these stars are pretty small for a lot of those. Kepler mostly looked at stars that are further away, so we found a bunch of them that are far away also. But now that TESS is operating, we will be finding more and more Earth-sized planets that are relatively close to our own solar system. So I think probably everybody knows how the transit method works, so I won't spend much time on this. Just again to point out that a Jupiter-sized planet around, transiting the sun sort of occults 1% of the area, whereas an Earth-sized planet, and this is actually a picture of Venus, which is an Earth-sized planet, transiting the sun, it only blocks 1/10,000th the light of the star for a solar type star. But of course, actually, this is more like the situation for the Earth crossing a red dwarf, because the red dwarf is, could be 1/10 the size of the sun. So that's why it's easier. And we do best from space for the reasons down here. You don't know when the planets are going to transit, although red dwarf planets transit more often. So you kind of need to be watching all the time. And you really want several transits before you're sure about it. And then this tiny amount of light that's knocked out means you can do better from space as well. So here's a summary of the kind of results that the Kepler mission got. This was NASA's big transit mission, was launched in 2009 and operated for 4 years in the prime mission, and then operated another 4 years in the K2 mission, which didn't stare at the same field. So in the first 4 years, it stared at the same field of stars, sort of never blinking except to squirt data down every month or so. And this is what it found. It found a lot of planets that were smaller. That was the point of the mission. These blue ones were the ones that were found by radial velocity, and pink ones earlier. And then the yellow ones are ones found by Kepler. And so it found a whole bunch of planets that are between the size of Neptune and the size of Earth, and also a bunch that are the size of the Earth and even smaller. And this part down here it was hard for Kepler. So this is very incomplete. So we have to correct the actual number of planets found here for the fact that they're harder to find. And we basically conclude that most planets are in this realm, sort of below the size of Jupiter, and there are probably as many down here as there are here. It's just that Kepler couldn't see them as well. Of course, we don't have any planets in our own solar system that are in this gap here, and so there's a question about what are those planets like. And one way that we need to find out about that is to actually measure the mass of the planet as well as the size. So Kepler gives you the size of the planet by how deep the dip when transit is, if you know the size of the star, and that we're pretty good at. And then the radial velocity method, or the wobble method, works with the pulling of the planet and the star, they both orbit the common center of mass. And so if you have both the mass and the size of the planet, then you can get its bulk density. And that of course, and that now lets you start looking at what kind of planet it might be. So people began, calling all these planets that were larger than the Earth but smaller than Neptune super Earths. But that was not really the right thing to do. The real question is, are some of them are super Earths, that is to say, terrestrial type planets that are larger than the Earth, but some of them are mini Neptunes, that is Neptune-like planets that are smaller than Neptune. And the question is, where's the dividing line? And once we started measuring densities of planets, this is what we found. So this is kind of what you expect rocky planets to look like, sort of in theory. If you make them have the same composition as the Earth, they would follow this line here. And these blue points are data points. And then here you see that this is the planet density on this side, and the planet size down here at about 1.5 times the size of the Earth, that is the radius of the Earth. The density started going down again. And these planets are more massive than these planets over here, but they're less dense. And how is that? That's because the density, remember, is the volume divided by the mass, or the other way around. And the size that we measure is just the size of the opaque planet. Where can't you see through it anymore? That's what blocks the light from the star. That could be the rocky part of the planet, but it could also be an atmosphere. If the atmosphere is cloudy, you can't see through it either. And then you get the size of the planet is influenced by the atmosphere. If the atmosphere starts to be an appreciable size of, appreciable radius compared to the planet, then the density is going to go down because the atmosphere has hardly any mass in it, but it has some radius. And that's what we think is actually happening here. So really appropriately, all these planets that are sort of more than 1.5 times the size of the Earth should be called mini Neptunes, not super Earths. And the ones on this side, less than 1.5 times the size of the Earth, are actually super Earths. Now, what kind of atmosphere would you have here? Well, as you know, the gas giants are mostly hydrogen and helium. The Neptune type planets start having, hydrogen and helium on the outside, and they have rocky and also sort of volatile, like water and methane and ammonia kind of materials inside. And so if you still imagine that there's a rocky planet here, but it's got a substantial layer of hydrogen and helium over it, that's not going to be a habitable planet. And the reason is that just the weight of the atmosphere, by the time you get to the surface, the pressure needed to support the atmosphere would be thousands of times greater than the pressure on the Earth, and consequently the temperature would be thousands of degrees at that surface, and so that's not going to be habitable. So the mini Neptunes that are found in the habitable zone are not in fact habitable, and people have not been terribly careful, especially the newspapers, about distinguishing between mini Neptunes and super Earths when people discover planets in habitable zones. So that's just something to keep in mind. Even if you have a terrestrial planet, if it's covered with water, and the water is a lot deeper than our water, so if it's, let's say, hundreds of miles deep, you're going to have similar problems at the rocky surface. The pressure is going to be too high, and proteins, for example, can't exist in water that high pressure. Okay, so let's talk a little bit more about this concept of habitable zone. It's not really a good name because we don't actually know whether planets in this zone are habitable or not. What it really means is if you took the Earth and you put it where this planet is, would it retain sort of surface life? Or another slightly more general way of putting it is, if the planet were Earth-like as opposed to Earth-sized, would it have long-term liquid surface water where it is around its star? that's really what is meant by habitable zone. Whether the planet actually has water or not is not a question, and or what the atmosphere is like or anything. And that's why the concept of habitable zone is a little misleading. It just means the temperature might be right, but even that's not clear, as I'll say in a second. So we don't know whether there's life on these habitable zone planets. You would at least have to know something about the planet's atmosphere to even get started with that question. And even the surface temperature is going to be a question, as I'll point out in a second. But the habitable zone defined this way does depend on what kind of star we're talking about. How luminous is the star? The more luminous the star is, the further away the habitable zone will be from the star, and also the larger the annular ring that constitutes the habitable zone. So here's a sun-like star, and here's one concept of habitable zones. People tend to draw the inner boundary of the habitable zone at about the orbit of Venus, because Venus isn't habitable. But that's also cheating a little bit. Okay, Venus isn't habitable, but if you had a different planet there, it might be. So that's again a question. But if you go to stars that are lower in luminosity, the habitable zone definitely has to move closer to the star. And these red dwarfs, as I said, are very faint, and so their habitable zones are very small. So they are quite close to the star, and they also don't cover much area. As you start thinking about it a little more, you realize that, okay, I've calculated the temperature the planet would have based on the amount of energy the star is giving it, but I haven't accounted for the greenhouse effect. And that's very important. For example, the Earth would be frozen without a greenhouse effect. We worry a lot about climate change and so on, but climate change is kind of a small tweak on top of our major greenhouse effect that we already have, that we're very glad we have. Otherwise, the Earth would be a snowball planet. And the main greenhouse gas for the Earth is actually just water vapor. And so we're glad that's there too. But if you're talking about exoplanets, you don't know what kind of atmosphere they have. If the Earth had Venus's atmosphere, that is to say it was mostly carbon dioxide, we'd be hotter. In fact, that's of course what the whole climate change debate is about. We're going to increase the amount of carbon dioxide a little bit and make it uncomfortable for ourselves. But Venus has, an almost pure carbon dioxide atmosphere. That would make it a lot more uncomfortable, obviously. And so people try to calculate habitable zones and then think about, well, okay, is there a strong greenhouse effect? And if so, where's the habitable zone? Was there a weak greenhouse effect? And so you can change where you think habitable zones are based on that kind of question. And unfortunately, for the most part, well, actually completely for terrestrial sized planets, we don't know yet what their atmospheres are like. So that is good to keep in mind as you think about habitable planets around other stars. So you can end up with, an Earth-sized planet that's almost the same distance as the Earth is from the sun, and that it's not habitable, or you could end up with a frozen Earth right where it is if you didn't have enough greenhouse. So that's one of the considerations. But there's some bigger ones that have to do with red dwarf habitable planets, and the sort of the biggest one is the planets are close enough to the star that it does the same thing to the planet that the Earth has done to the moon, and that's tidal locking. So the tides that the Earth raises on the moon basically take it from being a sphere to being slightly egg-shaped, and then the egg wants to point towards the Earth, and there's tidal dissipation mechanisms, and a long time ago the Earth managed to lock the moon so that one face always faces the Earth. The red dwarfs will do the same thing to Earth-sized planets in their habitable zone. So reasonably soon, the planet will find itself with one face always facing the star and the other face always facing away from the star. It's not that the planet isn't spinning, right? It is spinning. It's just that the spin period of the planet is equal to the orbital period of the planet. And so you have this tidally locked situation. So for a long time, people said, oh, well, that's crazy. You know, you couldn't possibly have a habitable planet if one side's always dark and the other side's always lit. Well, I mean, it does, of course, have a big effect on the planet's climate, but it turns out this is not a showstopper. But certainly the substellar point, you know, always gets the most energy from the star. And then when you get to the terminator, you know, you stop, the star sets basically here, except it doesn't set for people on the planet, right? They have to move. If you want the sun to set, you have to move over here to get it to set. And then on this side, you never see the star. And obviously that's going to be a lot colder than this one. And so the thing people worried about initially was, okay, on the dark side, there's no sunlight at all, no starlight. So it's just going to get colder and colder, and the atmosphere is eventually going to condense. You know, first you'll get dry ice snowing out, and then you'll get liquid nitrogen dropping out, and so on. And you know, you can collect the entire atmosphere onto the backside of the star in a frozen state, and that's obviously not habitable. So that was the concern. Luckily, it turns out that's actually wrong. So now that we have, you know, fancy climate models that we use to study climate change, you can take those models and put different atmospheres onto different planets and tidally lock them to stars and see what happens. And so models tell us that now, even if you just had the Earth's atmosphere and you locked the Earth to the sun so that one side only faced the sun, the atmosphere would not freeze out on the backside of the Earth. And the reason, of course, is just the atmosphere will get heated on the front side. It's cooling on the backside. So there's higher pressure here, lower pressure here. So a wind will start to flow, and the planet is spinning. And so you'll get flow taking heat from the lit side to the unlit side. And although it's obviously going to get very cold, right? So on Earth, right, we sort of have that situation. Antarctica doesn't see the sun half the time, and the Arctic doesn't see the sun half the time, and it's cold there. But it's, you know, the atmosphere doesn't freeze out, and that will still be true for these exoplanets that are locked, even with 1 bar atmosphere. And of course, if you have a thicker atmosphere, you're better off than that. So the temperature structure on a locked Earth-like planet around a red dwarf that's at the right distance looks like this. You basically have a big jet stream that carries heat around to the dark side, which is over here. And yeah, it's cold. It's colder away from the equator than at the equator. But it's you know, so here's the temperature scale for an Earth around a red dwarf, basically. Cold, but not fatally cold. Another question of interest for red dwarf planets is the star doesn't give you the same kind of light, right? So here's the sun, this black curve here. This is a K star for those of you who know spectral types, and this is an M dwarf or red dwarf here. And between these two vertical lines is where visible light is. That's what your eye can see. And you can see the red dwarf puts most of its energy out in the infrared, not in the visible, like the sun does. And that makes a difference too. So for example, so as I said, we don't really know what the atmosphere is like on these planets. And even if we knew that, we don't know what the surface is like either. You know, is it water? Is it land? Is it ice or snow? You know, all those things matter in terms of how much light gets absorbed from the star and how much gets reflected away. But for example, with snow, you know, the reflectivity of snow in the visible is almost 100%, as you all know. Snow is very bright. But in the infrared, snow is actually pretty dark. So if you had covered the planet with snow, it would absorb a lot more starlight than you might think, if it's a red dwarf star. So anyway, these are the kinds of things that we don't actually know the answer to yet for any of these exoplanets. And so my point is, we can talk about planets in the habitable zone, but we really don't know what the surface conditions are like, or what the atmosphere is like, or how much water they have, or anything like that. So while while it's promising, it's definitely not definitive. Okay, well, there's something else that we need to worry about too, and that is the stellar magnetic fields. So it turns out essentially all stars have magnetic fields. All you need to do to produce, and these are magnetic fields that are being continually regenerated by the star, you need to have a conducting fluid, you need to have convection or boiling motions on the star, and the star has to rotate. Well, stars are plasmas, so they're definitely conducting fluids. That is to say, the particles are charged. Any solar-like star, so stars that are sort of 2 solar masses or less, will have convection at the surface, and all stars rotate. And so you're going to get magnetic fields on all these stars of interest. And so for stars with surface convection zones, the fields become visible. They pop out of the surface, and they have a number of effects. And of course, you're all familiar with the solar cycle. Basically, the field can start sort of like a dipole, but then the star is also differentially rotating, and it pulls the field out into distorted configurations. And then those configurations produce currents, and there's heating, and we get a bunch of interesting effects. And so the sun is an example of a magnetic star, obviously. So here it's quite obvious that the magnetic fields are controlling the plasma above the surface of the star. You see these loops that come from bipolar regions. So there's a north pole and a south pole, and the loop connects them, kind of like iron filings do on a bar magnet. On the sun, these are pretty big scale things. Here's the Earth compared to a set of loops. And when these loops get twisted up too much, they can erupt and explode and fire off a lot of plasma into the interplanetary medium. Also, the fact that these pictures, by the way, this picture is taken in X-rays. This picture is taken in UV. So you can see the sun is very bright at these high energy wavelengths, which you would not expect from a 6,000 degree star. So, the temperature here is a couple million degrees. The temperature here is tens of thousands of degrees. That produces UV and X-ray radiation, and that will also impact the planet. So you have both high energy photons and also high energy protons and other particles coming, all due to the fact that the star is magnetic. The most extreme example of these is what we call flares, where loops get twisted up enough that they resolve themselves into a simpler structure by dissipating a bunch of the magnetic energy. And that produces the largest explosions in the solar system. Basically, the output of the sun is matched by a flare for some short amount of time. So that's a lot of energy. And it turns out the sun is a pretty wimpy, tired, low-key magnetic star compared to a lot of other stars. And in fact, the sun itself was far more active when it was younger. So we know that stars lose magnetic activity over time. But basically, the reason is the magnetic field creates the solar wind. The solar wind actually carries off angular momentum, and the star spins down. And basically, the faster you spin a star, the more field you get. So they're faster spinning and strong fields when they're young, and they slow themselves down over time. And the sun is pretty slowed down at this point. Red dwarfs have a reputation of being much more active than the sun, although it's not. That's a little more complicated, but I'll come back to that. But on younger stars and on red dwarfs in particular, you can get flares that are 1,000 times more energetic than the biggest flare we've ever seen on the sun. Actually, Kepler discovered that even solar type stars can occasionally do this. And so people have been worrying about, gee, does the sun do that every so often? And if it did, it would wipe out our entire satellite fleet and our electric grids and everything. We don't think this happens very often, and maybe not at all anymore on the sun, but certainly not more than once every several thousand years. A youngish red dwarf, on the other hand, can pop these things off, daily. So that's definitely extreme. And remember, we moved our habitable planets much closer to the star. So the red dwarf is much less luminous than the sun, but it is not much less magnetically active. And so the planet is now being subjected to the same kinds of things the sun throws at us, only much more often, and the planet's much closer. So that's the other sort of big concern about habitability of red dwarf planets. So, I mean, in some cases, and in fact, Proxima Centauri, the closest red dwarf to us and the closest star to us, recently got brighter by 50 times. That is, the whole star got 50 times brighter for a couple hours due to a huge flare that went off on that one. Okay, well, what does that do to planets? In our case, the Earth's magnetic field is, we've got our shields up, basically. The Earth's magnetic field is enough to divert most of the solar wind around us. So we have a magnetosphere around the Earth, and charged particles from the sun mostly flow around us, although sometimes they can sneak in the back of the tail here and come back down over the magnetic poles. And then, of course, we get the aurorae. So the auroral ring is just the Earth's field near the poles where these particles, they get in back here and they come back around and come back down and hit our atmosphere, and that makes the aurora. Do exoplanets have magnetic fields? Well, we don't know. Probably, they probably do. They probably have structures similar to the Earth. The ones orbiting red dwarf stars in the habitable zone have longer days, basically. Well, of course, their day is infinitely long, but they have longer rotation periods, because the orbital periods are for habitable zone around red dwarf is a couple weeks. So they might not have as strong a fields, because remember, rotation matters. We don't know yet, but this is an important question as well. So what we do know is stellar magnetic activity can be deadly for planets, because we actually see evidence of it directly from some close-in planets. So the steady flow of high energy photons basically will break apart molecules in the atmosphere of the planet. And once they're charged, you have charged particles now, you strip the electrons off and make the molecules or atoms ions. They can get picked up by the stellar wind and taken away, depending on the magnetic field of the planet. But we definitely see evidence that planets are losing atmosphere when they're close to their magnetically active stars. So that's not a question. That definitely happens. And in fact, it's actually happened in our solar system. So Mars has lost almost all of its atmosphere. I'm sure you know that early Mars, had water, liquid water on it, and a thicker atmosphere, and it lost it. And the reason it lost it is partly because it's a small planet. Its magnetic core froze early, lost its shields, and then the sun just started stripping atoms off of Mars' atmosphere. Now Mars, has another excuse, which is it's smaller than the Earth, so the gravity isn't as strong. So it's not clear if you swap Mars and Venus, for example, their habitabilities would both be different than they actually are. But at any rate, we actually can see the sun stripping Mars's atmosphere now. There's a spacecraft that actually studies this and it sees it happening in real time. And of course, the other Earth-sized planet in our solar system is not habitable. And that's also due to the stellar magnetic activity. So Venus is an Earth-sized planet. It has a thick atmosphere, so it hasn't lost its atmosphere. Here, the problem was it lost a very crucial component of its atmosphere, namely hydrogen. So we know that there was water on Venus at the beginning. And what happened, the Venus and the Earth probably started off somewhat similarly. But on the Earth, what happened is you got the oceans condensed out. And so you had liquid water. Carbon combined with the water to make carbonate rocks. And you took almost all the carbon dioxide out of the Earth's atmosphere. So the Earth and Venus have a similar total reservoir of carbon, but it's all in rocks on the Earth and it's all in the atmosphere on Venus. So Venus's atmospheric pressure is 90 times the Earth's because essentially it didn't take the carbon out and make it into rocks. Why didn't it? Well, it was closer to the sun. The water remained as steam. And then the sun was far more active early on and Venus was closer. And basically it kept breaking the water up into hydrogen and oxygen and then stripping the hydrogen. And finally, Venus ended up with essentially no hydrogen. The other problem with Venus is it's rotating a lot more slowly than the Earth. The rotational period of Venus is hundreds of days, hundreds of Earth days. So it didn't have much of a magnetic field either. Those two things meant that Venus ended up quite uninhabitable. And that just goes to show you that just because a planet is, a similar distance from the star doesn't mean it's going to look the same. So we try to be careful to say Earth-sized planets, not Earth-like planets, because we don't know if they're Earth-like or not. So that's the big question, really, not the tidal locking so much anymore, but the stellar magnetic activity. And in particular, can water survive the early stellar phase when we know the star is incredibly magnetically active? And in the case of red dwarfs, there's another problem I'm going to get to the next slide. It's slower to let the planet become in the habitable zone. I'll explain that in a minute. And then the other question is, and what about planetary magnetic fields? Presumably, if you have a strong enough field, you can survive this, and if you don't, you probably won't. So those are the big questions. We're trying to learn more about that in astrophysics right now. So let me explain this problem of red dwarfs in particular. Remember, I said they live a very, very long time. They do everything slowly, basically. So they live a very long time. They also take a long time to settle down to the main sequence, and they take longer to spin down and lose their magnetic activity. So part of the reason they have a reputation for strong activity is they keep it longer. They do eventually lose it, though. We do know that. But at the early part of the stellar evolution, here's what happens. The star is actually shining not mostly due to nuclear fusion, but just due to gravitational contraction. And this is true for the sun as well. But a sun-like star, so here's the age in millions of years, starting at 0 when the star forms. And the sun was originally, tens of times more luminous than it is now because of gravitational contraction. But it contracts down pretty quickly. And so after 10 million years or so, it's pretty close to the main sequence. That is to say, it's pretty close to its stable luminosity. For a star that's half the mass of the sun, though, this process occurs more slowly. So here we are out at 30 million years, and it's still 3 times brighter than it's going to be. And for these red dwarfs, so these are the red dwarfs here. For the low mass red dwarfs, this process takes hundreds of millions of years. Now, why is that a problem? Well, the habitable zone is defined by a comfortable place for the planet when it reaches its stable, when the star is at its stable luminosity. So while the planets form sort of in this time period here, and their stars are too bright there, so they're going to be, the water wouldn't be liquid then. It's definitely going to be a steam atmosphere, and the star is really magnetically active. So this is, in terms of if you want to lose your water, this is a great situation. You're going to have plenty of time to strip it. And so that's a big concern about red dwarfs as well. All right. Well, if that was just the story, then we'd probably say, well, no, red dwarf planets aren't habitable. They'll lose all their water. But there are various ways that one can imagine that one might end up with a habitable planet. And I'm just going to go through a few of these. None of these are, either very well developed or do we have any actual evidence for them. But they're clearly plausible things that might happen. And we're going to be trying to find out, how often they do happen. So one easy solution would be just replace the water that gets stripped by the star with water that's inside the planet. that comes out later on when the star has settled down. And the larger the planet mass is, the more likely it will have, enough water to make oceans like the Earth's oceans. And also larger planets are geologically active for a longer time. So this seems entirely plausible, frankly, for planets that are Earth-sized or 20% bigger or whatever. And remember, you got as much time as you want with red dwarf. The star is going to last. The planet will completely freeze its core and everything long before the star does anything. On the other hand, if it takes 10 billion years, then it means red dwarf planets are just becoming habitable now, because that's the age of the universe. And when you talk about red dwarfs, you need to have a more expansive timescale in mind. Well, here's one that kind of flips the tidal locking thing around. So what about storing the water on the dark side of the planet, right? Because remember, we were worried that the atmosphere was going to freeze out. Well, the atmosphere is not going to freeze out. Water is, though. Water will freeze out, no problem. On the backside, it freezes out in Antarctica. And so, as the planet circulates the atmosphere, it's going to tend to snow on the backside for sure, because it's pretty cold back there. And it'll just collect there. You have an increasing ice pack or ice mass on the backside, and only the top of it is subjected to even any heat from the atmosphere at all. So definitely the planet will probably store a bunch of water on the backside. Now, the water that comes back around to the front, some of it would be lost due to this activity, stellar activity. But you have a large reservoir until the star settles down, and you can, and once it's settled down, the stuff that comes back around to the front is okay. You can imagine, making the planet, hydrating the planet again, and you have a huge supply of water on the backside. There's some astrophysical schemes as well. One is you might just bring the water in later. The planet loses the water that it had, but if you keep hitting it with comets have plenty of water in them, you can rehydrate it that way. In fact, we're still arguing about whether the Earth was hydrated by being hit by comets later, as opposed to having the water intrinsically in it. This is still a big debate. We don't actually know the answer. So comets can definitely hydrate planets. And red dwarfs have many fewer Jupiter mass planets than sun-like stars do. So what that means that the comet belt basically is not going to get thrown out to the Oort cloud as it did for the Earth or by Jupiter. You'll have lots and lots and lots of comets orbiting outside, outside the habitable zone that can slowly find their way in, some of them. So that's plausible. We also know that planets migrate due to interactions with other planets. So you might have a planet that's out in the safe zone, plenty of water, way too cold to be habitable, that ends up finding itself later on closer to the star where it can be habitable. Now that's presumably doesn't happen that often, but it certainly could happen. So that's a possibility. Oh, and I already talked about the cold trap. Or, we definitely know this happens. You can start with a mini Neptune and let the star ravage it. And in fact, as I said, we have direct evidence. We can see mini Neptunes that are losing vast amounts of hydrogen near their stars. And in fact, the statistics of mini Neptunes shows kind of a desert. So you see a bunch of mini Neptunes down to a certain distance from the star, and then there's kind of a gap, and then you have more sort of super Earths. So it's pretty clear that there is a zone where the star will, in fact, strip a mini Neptune down to a super Earth. And so if it's the right amount of stripping, you can end up with a nice amount of hydrogen on your planet where it had too much to begin with, and the star fixed it for you. Right? All of these are just possibilities. We don't know how often they happen. We don't know what the history of any particular exoplanet is at the moment. But my point here is that one shouldn't give up on red dwarf habitable planets. There are ways in which that could happen, and we have to find out how often they end up habitable. So you can think more about what these planets might be like. For one thing, of course, the front side could be too hot and the back side too cold, but somewhere near the terminator, it could be, the right temperature, because you have this temperature gradient, basically. So maybe, it's only habitable near the terminator. I don't know if that's all that likely, but it's a fun idea. Also, remember, you put planets can be found sort of any distance from the star. So let's say it's kind of too far away, so most of it's frozen. But remember, the substellar zone is hotter, so you could imagine something like this eyeball planet, where there's an ocean on the planet. Most of it's frozen on the outside, but there is a zone of free water. And in fact, there was a recent paper discussing, the sea ice, would it cover this or not? And people are starting to think about these things more carefully. So you can always put a planet at the right distance to get this, if you get to place it wherever you want. Also, a lot of climate work's being done, and recent work suggests that the star-facing side of the planet is going to be much cloudier than the backside. Basically, the clouds will condense out. The front side could be quite cloudy, so that blocks some of the stellar light, and also protects the surface from some of the stellar high energy radiation and so on. So, like I said, we're just starting to think about these things. It may well be that that we should think about planets as being habitable further out than we do at the moment, especially depending on what the greenhouse effect is. And then the dark side of tidally locked planets could be a habitable zone. That you've probably heard speculation about life on Europa, for example. Here, Europa is totally not in a habitable zone, right? It's out by frozen Jupiter. It's also subjected to incredible high radiation from Jupiter. However, it's got an ice shell of at least 10 kilometers thick, and below that, we know there's an ocean, a salty ocean, and below that, there's definitely a volcanically active rocky planet, or moon in that case. And the thinking about life on Earth is it probably started at deep sea volcanic vents. So this, the backside of tidally locked planets might be habitable zones in that sense. If there's an ocean, it certainly will be frozen for some distance down, but the planet is geologically active. It can also keep the bottom of the ocean liquid, and especially planets that are larger than the Earth will have plenty of volcanic activity at the base of the ocean. So why not? In this case, all the considerations about the star don't matter, basically. In fact, we of course don't have to really put the planet in the habitable zone at all. And it certainly doesn't care about the flares or any of the high energy radiation, because it never sees the star. Also, there's an ice shell, so those considerations just go away. And the life on the planet might not care about the planet's atmosphere or the star, which means that the whole concept of habitable zone isn't really habitable zone, right? It's possible that the main habitable zones in the galaxy are in fact under ice shells at volcanic sites at bottoms of oceans. That there's no reason to think that's not the case at the moment. We just don't know. Okay, I'll finish the talk by talking about a few of the most promising candidates that we have for nearby habitable planets around red dwarfs. In fact, the very closest star to the Earth, Proxima Centauri, has an exoplanet in the habitable zone. We don't know a ton about this planet. We know what distance it is from the star. We know it's in the habitable zone. We know it has at least 1.3 Earth masses, and it probably is less than 3 Earth masses, which puts it in the sort of super Earth category. But it's not a transiting planet, so we actually don't know what the size is, so we don't know the density. Turns out Proxima, we found 2 other planets there as well. One of them is very close, so it's much too hot. and the other one is pretty far away, so it's too cold. But that's 3 planets right there around Proxima. And I also want to point out that Proxima is actually a distant companion to what people usually say is the closest star to the Earth, Alpha Centauri, which itself is a binary, actually. So there's Alpha Cent A and B. Alpha Cent A is very solar-like, but it's a little older than our sun. Alpha Cent B is a little less massive than A. We don't know planets around them yet. The orbital period of these two around each other means that you could have a stable planet, sort of 1 AU from A, but it's obviously a more complicated system. So Proxima is definitely a red dwarf. It's much smaller than it's much fainter than Alpha A or B, and its habitable planet is very close. So here's the orbit of Mercury, and here's the planet that we know. But we don't know it that well, so we can do better than that. Better case is called LHS 1140b. This one we know quite a bit about. So first, it's also orbiting a very low luminosity red dwarf. So here's a distance scale. This is 0.05 AU and 0.1 AU. And here's where this planet is. So in the habitable zone, these are the sort of inner boundaries and outer boundaries, depending on what you assume. It's nice smack in the middle there. So that's cool. We do know its diameter because it is a transiting planet. So it's bigger than the Earth, but not 1.5 times bigger. So that's good. Yeah, it's much closer. And its year is 25 days, basically, which of course would also be the spin period for this planet. So here's what the transit of that planet looks like. But here also is the radial velocity signal from that planet. So we know what its mass is as well. So it's 6.6 Earth masses, but 1.4 Earth radii. So this really is a super Earth. And actually, when you compute the density, it is like iron. The density is like 8 grams per cubic centimeter. So it's actually one of the densest planets we know. If you were on the planet, the surface gravity would be something like 3 times that of Earth. Does it have liquid surface water on it? That we don't know. Right? And why is it so dense? And is it such a dense planet weird in other ways? We don't know. But this one has got all everything we do know. Makes it a sort of super Earth and habitable zone that is of great interest. And then probably most of you know about this. This is an amazing system. This is around a really low mass red dwarf. It was actually discovered from the ground. So it's called TRAPPIST-1 because the observatory is the Trappist Observatory, which was named after Trappist beer, actually, which is made by Trappist monks. So that's why the weird name. But then it was studied from space and turned out to have seven planets, all of which are, not that different from Earth size, basically, and 3 of which are kind of in its habitable zone. I mean, in a way, it looks a little bit like the Jovian system. So here's these are to scale. This is the sun. This is TRAPPIST-1, the star, and here's Jupiter. So you see, it's not a lot bigger than Jupiter, but it's a lot more massive than Jupiter. So the star is much more dense than Jupiter is. And then Jupiter has these 4 Galilean moons that are not Earth size, but 2 of them are bigger than Mercury. And then TRAPPIST has these 7 planets, and it's clear that they're not in order of size or composition or density, and that's been a result from Kepler. Is we don't quite understand why it is that the solar system looked so nicely organized, but it turns out exoplanetary systems are not necessarily well organized, and of course the whole system is tiny compared to the solar system. But as I said, the habitable zone, which is E, F, and G here, these planets are within it. And a couple of them show signs of water in their atmospheres. So, this is a great system, and it's pretty close to the Earth. Now the TESS satellite is discovering a lot more planets around red dwarfs that are, within 50 or 100 light years of here. So it's clear that, this kind of deal is not very uncommon. Okay, so that's the current state of affairs about red dwarf habitable planets. This is an artist's conception of what the potentially maybe habitable planet around Proxima might be like. Obviously, this is entirely artist's conception. Here's the red dwarf Proxima Centauri, and here's the binary system Alpha Centauri A and B. So it just happens that Proxima is on our side of that. So that does make it the closest star to us. There's reasonable chances that we'll be able to study this planet in more detail because it's so close to us. We need to do a little bit better job on interferometry, and then we might be able to actually image the planet, get its spectrum. And there's even of course, the Breakthrough Starship wants to launch little tiny chips at a fraction of the speed of light and pass them by this planet to see what it's like. That's still more or less a dream, but people are working on it. So I'll stop there and take questions. Thank you.
Thank you very much, Dr. Basri. So we got any questions here? Oh, yes, we got plenty. All right.
Okay. So
Okay.
what
I
is
don't
the
break-
difference in composition from the sun to a red dwarf? And the second question is James Webb going to be useful for studying these things, especially Proxima and the closer exoplanets? And then the third thing is all these planets probably have moons, and what about life on their moons?
Yeah. Okay. Well, the first question is easy. Red dwarfs have basically the same composition as more massive stars. They're just smaller. They're less massive. But they're similar composition. And of course, all sun-like stars don't have exactly the same composition. Some are what we call metal poor, some are metal rich, some are like the sun, and that's also true of red dwarfs. But they're essentially hydrogen and helium and trace amounts of other stuff. So that's not different. What is different is the lower mass means two things basically. One, that the nuclear reactions in the core go much slower. And the second thing is the red dwarfs, the lower mass. So red dwarfs are between half and a tenth solar mass. You go below about a third of a solar mass, the red dwarf is fully convective. That is, the entire star has these boiling motions, which means that all the hydrogen in the star can be used over time. It'll visit the nuclear core and be burned. Turns out the sun only burns about 10% of its hydrogen, and then it can't get at the rest because there's not convection on the inside. So they burn a similar amount of fuel actually, but the red dwarfs burn it much more slowly. So that's why they live longer. The second question was, I remember the third question.
And Webb study.
Oh, he wanted to know how Webb is going to contribute.
Right. So Webb is definitely going to start giving us information on planetary atmospheres. It will have trouble with sort of Earth-sized planets, but it will try, and it will definitely succeed at sort of Neptune-sized planets or mini Neptunes around bright stars. So TESS is up there to collect targets for Webb. That's one of its purposes, and it has a bunch. And so what happens is that when the planet transits in front of the star, some of the starlight actually goes through the planetary atmosphere, and Webb has the spectroscopic instruments to study what the light does as it goes through the atmosphere, basically. So it'll definitely be getting us atmospheric compositions for Neptunes and some mini Neptunes, and it'll try the TRAPPIST system. It's a hard road to hoe, but it's gonna try. Yeah. And there was a question in between that I can't remember, but.
Life on the moon.
Oh, the moons, right.
That-
Yeah, so probably a lot of these planets have moons. We haven't been able to find them really, except that there's a couple of proposed sort of Earth-sized moons around sort of Jupiter-sized planets that may have been detected with transit. It's a tough problem because the moon's not in the same place. Each time the planet comes around, the moon might be behind the planet or on one side or the other, or near it or far from it. So it's a difficult observation. But people are still working on that. But we have no reason to think they don't have moons, especially the more massive planets. Earth-sized planets, it's not as clear, right? Venus doesn't have a moon. The Earth only has a moon because it got whacked by another object. So we're less clear on that one.
Hey, I got another question here for you.
So I have a couple of questions. The first one is about the tidal locking. So if the planet has an axis of rotation which is not vertical, is it slowly tilted toward until it becomes vertical? And then the second question is, what about binary red stars? Have we have any information on those? And are there red star mergers? And what one star is stealing material from another red dwarf in a binary system?
Yeah, so the first question is about planetary obliquity. So yes, what happens over time is the obliquity gets regularized. As I said, essentially the planet gets distorted into an egg shape, and then the egg wants to point at the star. So that takes care of both things, the rotation period and the obliquity. So yeah, we would think they would be pointing at the star. As far as binaries are concerned, so solar type stars, about half the solar type stars have a binary companion. It's more like a quarter of the red dwarfs have a binary companion. So they're a little less prone to binarity, but there's still plenty of them. And then again, it matters. What matters is how separated the binary pair is. So essentially, you can have stable planetary orbits if the orbit is less than a quarter the separation of the binary, or more than 4 times the separation of the binary. So you can put a planet around both of them, or you can put a planet around one of them, as long as you satisfy those basic conditions. And we do know, of planets that are in both situations. In terms of mass transfer, so the red dwarfs don't evolve to red giants, right? Remember I said the first one to die will die at 10 times the current age of the universe. So none of that's happened yet that way. But of course, what has happened is red dwarfs that are in binary orbits around more massive stars, the more massive star will swell up to be a red giant and can transfer mass to the red dwarf, but not the other way around so far.
Okay. Oh, we got a question. I haven't seen anybody on chat yet. Is there one? No, that was from earlier.
Oh, somebody asked me if the sun has more convection than a red dwarf or less.
Oh, there it is. It's right.
The fraction of the sun that is convecting is less than the fraction of a red dwarf that is convecting. And if the red dwarf is less than about 1/3 the mass of the sun, then the convection the star is fully convective. So the convection reaches all the way to the center. For the sun, it's only the outer 30% or so that is convective, and the inner 70% is radiative. So the gas is not overturning, and the energy is just being transferred out by photons, by radiation. But as the star's temperature is lower, it's harder to push the radiation through cooler stuff, so it tends to convect more. So also red giants are more convective. And then if you get hotter than the sun, the star is even less convective. So the convection zone disappears entirely at sort of early F to A stars. They're so hot they just transfer everything by radiation. Except actually, the other thing that happens is their nuclear burning core is so bright that it convects. So they have inner convection. They have convective nuclear cores and outer radiative envelopes. That's a little in the weeds though, right?
Wow. Okay. Got another one for you here.
You there?
Yeah, yeah. Mhm.
Hello, Dr. Basri.
Right.
Is our sun a part of a binary? And then the second thing is, can telescopes get good enough to see physical features of other planets?
Okay. Well, I sort of answered the binary question before. But I'm not sure if you wanted to know something else about that. But in terms of the second question, in order to see physical features on planets, if you want to image them, then essentially you need a huge telescope. But you don't have to build the whole telescope. So this technique of interferometry is what gave us the picture of the black hole that was just published a couple of weeks ago. Essentially, they have radio telescopes, 10 of them say, spread at different places around the Earth, and they can combine the signal to make it as though it was an Earth-sized telescope, most of which is missing, and you only have these tiny little pieces here and there. So that technique is called interferometry. And so if we can do interferometry from space, you need to go to space to do it in the infrared and optical. So it's easier to do at radio wavelengths. If we can go into space and do that, and people have plans to do so, it's tough. I mean, there's some technology that has to still be developed. But then in principle, yes, then you could start seeing physical features on planets. But the other technique that people are thinking of will work earlier is, and they've done this, they've looked at the Earth shine on the moon and asked themselves, well, okay, so the moon is reflecting light from the whole Earth. And that's a little like, seeing a point of light. It's the planet. But the Earth is, rotating, and sometimes there are continents that are more prevalent, and sometimes there's ocean that's more prevalent. Do we see a difference in the Earth shine, depending on what part of the Earth is facing the moon? And the answer is yes. You can develop a little bit of a sense of the features on the planet. At least you can tell what the planet's rotation is, and that there's more reflective and less reflective parts of it. Now, of course, that assumes the planet's not just totally covered with clouds, and we've been having trouble with that. So some of the exoplanets that have been studied with transit spectroscopy haven't yielded much. All we've yielded is, oh, this is a very cloudy planet, and you don't get to see what's in the atmosphere. But yeah, there are various techniques, and people are working on them.
Okay, we got another one for you.
So when a star like the sun is first forming out of its disk, does it start out as a red dwarf, then eventually get to accumulate enough mass to become a star like the sun?
Well, of course, it does build up mass over time. It's not a red dwarf though, because remember when the star is forming, it's actually very, very puffed up, and it's shining by gravitational contraction. So it'd never be a red dwarf. We call them pre-main sequence stars, basically. So that when the sun was very young, hadn't settled down yet, it was actually 2 or 3 times bigger than it is now, and 10 times brighter. So that's not a red dwarf, obviously. And then it contracts down and settles down. And the red dwarfs also are, bigger and brighter when they're pre-main sequence, and then they settle down to be what they are today. So it's a little complicated, but yeah, at some point, the forming star has only half a solar mass or only a third of a solar mass. That phase though is pretty fast, and it doesn't look like a red dwarf.
Okay. We got one? Oh, good. I can't. Wow. And now we can even see it.
You mentioned that Proxima Centauri is the closest star of the Alpha Centauri group of three stars.
Yeah.
It'll always be so. If they're gravitationally bound, aren't they going to be rotating around each other?
That's a good question, and the answer is probably yes. But The distance between Proxima and Alpha Centauri A and B is 40,000 AU. So the rotation period is kind of, almost meaningless. It took quite a study to determine whether Proxima was actually bound to Alpha Centauri or not. But with Gaia and so on, now we're convinced they move together. But in terms of orbital period, boy, it's super long. The system might get disrupted by galactic tides before it makes one orbit.
All right.
Thank you.
Wow, okay. All right. I don't see anything on the chat.
I have one quick
You
question.
do, okay.
Like Sean
Go
has
ahead.
a question.
Can you hear me? So if these exoplanets are tidally locked, is there a chance that any of them have a strong magnetic field, or is that very unlikely?
No, I mean, we don't really know. It's true that their spin periods would be longer than the Earth's. But we don't really have good examples of planets that are with 2-week periods. And the vigorousness of the convection matters also. So if it's a more massive planet, it's going to be transferring heat out faster. And it might have a bigger iron core. So we're not really willing to say that. I mean, yeah, we don't want to say, no, they don't have magnetic fields yet. We'd like to try to measure them and find out what the answer is.
Okay. Well, I think, did we run out of questions? I guess so. Okay, well, thank you. Eric.
Thanks for having me. And
All right.
it was fun. Bye-bye.
Okay, this will be posted later on our YouTube channel. And with that, I would call it an evening. Thank you, guys. Appreciate it. Good night.